We possess a complex biological operating system tuned for spoken language, but spoken language is transient. Every word you speak vanishes the moment the sound decays in the air. To build communities that could survive beyond a single memory span, humans had to do something unprecedented. They began recording information outside the brain, on clay, bone, stone, and eventually papyrus. This was not just a new form of communication, it was the birth of an external memory system. The invention of writing set up a new developmental environment. In literate societies, children who learn to read show measurable physical changes in their brain connectivity. Cultural symbols force the brain to recycle older circuits for a new purpose, turning etched marks back into speech. In this video, we observe the ghost in the clay. From the geometry of the first marks, to the physical rewiring seen in literate brains, to the quiet trade-offs of living in a world where almost all human knowledge sits outside the skull. For hundreds of thousands of years, prehistoric language was primarily spoken. It was an acoustic phenomenon, bound by the strict limits of the present moment. Spoken communication depends on short-term memory and sustained attention. Without active rehearsal, sequences of words, facts, and numbers naturally decay within seconds. For the vast majority of human history, almost all collective knowledge lived within the human neocortex. Every shared technique for crafting tools, every medicinal recipe, and every ancestral lineage was stored inside biological brains and transmitted by voice alone. It was a closed loop of sound and memory. But as human populations transitioned from foraging to settled agriculture in regions like ancient Mesopotamia, the demands on that biological storage shifted. The volume of information that a society needed to track multiplied. Grain harvests had to be measured, central storehouses had to be inventoried, trade relationships had to be managed, and seasonal debts had to be recorded. Oral specialists, the bards and local officials, were capable of memorizing vast amounts of material. They were the living archives of their time. Yet there is a practical ceiling to what a single human mind can hold and pass on to the next generation. More importantly, a community relying solely on acoustic memory remains vulnerable to the physical world. If a famine, an epidemic, or political upheaval strikes, entire chains of generational memory can be erased in a single season. If the memory keepers fall, the contracts, the communal inventories, and the history die with them. It is in this context of growing administrative pressure that we see the first deliberate attempts to secure data. Early accounting systems, simple tally marks carved into bone, small clay tokens representing quantities of livestock, and impressed markings on mud tablets begin to appear. This was not yet literature. It was an emergency backup system. Recording information in durable media was a practical mechanism to bypass the biological ceiling, extending memory beyond the lifespan and the cognitive limitations of any single human brain. You have likely experienced this underlying limitation yourself. When you hear a long, unfamiliar sequence of numbers once and find that you cannot repeat it just 10 seconds later, you are colliding with the basic capacity limit of your phonological working memory. Spoken data is powerful, but it is fragile. It simply cannot scale to manage the intricate logistics of a growing civilization. This biological bottleneck forced human beings to look outside the skull. We needed a more stable container for human thought. And so, we began to inscribe our memory into the raw materials around us. Across different regions of the ancient world, communities began experimenting with marks. We see tally notches carved into bone, complex systems of knotted cords, small clay tokens used for accounting, and eventually fully formed writing systems. In the river valleys of Mesopotamia, these diverse experiments crystallized into cuneiform, constructed from distinct wedge-shaped impressions pressed into wet clay tablets with a blunt reed stylus. But if you look closely at these early scripts, you notice something fundamental. The shapes they chose are not random. Many of these early writing systems rely heavily on straight strokes, clean intersections, and clear, defined boundaries. These are forms that survive well in baked-in clay, but more importantly, they are forms that are exceptionally easy for the human eye to separate and identify. Visual neuroscience reveals that the primate visual cortex is fundamentally tuned to detect specific features in the environment. It actively searches for edges, junctions, and stark contrasts. These are the visual signatures that are common in natural scenes: the line of a horizon, the intersecting branches of a tree, the edge of a rock. And they are exactly the features that dominate many early writing systems. By relying on simple line segments, sharp angles, and repeated geometric motifs, these early scripts exploited pre-existing biological biases in the visual system. Without knowing the underlying neuroscience, early scribes intuitively designed writing systems that aligned with how the human eye already tracks contours and contrasts. They engineered scripts that could be recognized quickly and consistently. They took a landscape of raw mud and turned it into a landscape of legible geometry. When you recognize a modern road sign or a high-contrast icon instantly from a distance, your brain is utilizing the exact same neural machinery that once helped your ancestors detect the outline of a tree or the silhouette of an animal against the sky. Today, that ancient survival mechanism also processes letters and symbols. The clay tablet was a good match for the eye. But seeing a mark is not the same as understanding it as language. To turn geometry into speech, the brain had to reconfigure its own circuitry. It is easy to assume that reading is a natural human ability, much like walking or speaking, but this is an illusion created by modern education. Spoken language emerges reliably in children across all cultures, given standard social interaction and exposure. Reading, on the other hand, must be taught explicitly. It requires deliberate effort, formal instruction, and it does not appear in every human society. Writing is only a few thousand years old. In evolutionary terms, that is far too recent for a specialized reading center to have developed in the brain through the slow process of natural selection. When neuroscientists examine brain imaging of adults who have never learned to read, they find no region exclusively dedicated to processing written words. So, how do we read at all? To make sense of script, the developing brain must physically repurpose its existing circuits. In literate adults, researchers point to a specific patch of tissue in the left ventral occipito-temporal cortex, often called the visual word form area. When you look at text, this area responds strongly to written words and familiar letter strings. Originally, this region evolved to support complex object and pattern recognition, like distinguishing individual faces, identifying animal tracks, or categorizing tools. But during the rigorous process of learning to read, this area is recruited and reorganized to recognize the recurring visual patterns of human script instead. Structural and diffusion MRI studies reveal something even more profound taking place beneath the surface. Learning to read physically strengthens and refines the white matter tracts, the insulated biological wires connecting this visual region to the language centers in the temporal and frontal lobes, as well as the motor regions responsible for speaking and writing. Literacy is not a genetic inheritance written into a specific locus. It is, in a very real sense, a learned biological hack. It is a complex anatomical bridge constructed during childhood development that converts silent geometric shapes into internal speech. When you look at a page of text and hear the words echoing in your mind without ever moving your lips, you are experiencing this learned bridge in action. You are feeling your brain translate static visual patterns into simulated sound. Once the brain built a bridge from eye to voice, writing became a powerful extension of speech. But any reallocation of neural resources comes with subtle trade-offs. Centuries after the first scribes pressed reeds into wet clay, and long after writing had become common across parts of the Mediterranean, the Greek philosopher Socrates offered a stark warning. As recorded by his student Plato, Socrates criticized the invention of writing. He argued that it would encourage forgetfulness, planting a false conceit of wisdom in the minds of the young. People, he warned, would rely on external signs instead of rigorously training their own internal memories. It is deeply tempting to dismiss this as mere nostalgia, the complaints of an ancient oral culture facing an inevitable new technology. But from a purely cognitive perspective, Socrates was describing a very real shift. When reliable external storage exists in the environment, the incentive to maintain vast internal stores of verbatim knowledge simply decreases. In the palace economies of the Aegean world and the sprawling temple bureaucracies of the Near East, scribes utilized clay tablets and papyrus to keep exhaustive accounts, track complex tax obligations, and preserve long lists of goods. Once that data is safely recorded in a stable external medium, individuals no longer need to rehearse it constantly to keep it from decaying. The cognitive resources that might have been spent on the sheer metabolic effort of memorizing long texts, lineages, and ledgers are freed. They can instead be redirected toward other tasks: strategic planning, logistical inference, and cross-referencing written records to find new patterns. Writing does not erase human memory, it reallocates it. It shifts the primary balance of human cognition from internal storage toward external documentation and internal interpretation. You can likely see this very trade-off in your own life. Many people can still flawlessly recite the phone numbers they learned as children, simply because those numbers had to be rehearsed often before the era of digital contact lists. By contrast, we rarely memorize new numbers today. We depend on our devices to hold them, and our brains silently adapt to that environment by rehearsing them less. Writing allowed ancient societies to stabilize vast amounts of information outside the skull. But in our time, that offloading has accelerated to an entirely new extreme. Clay tablets and fragile papyrus scrolls were just the beginning of this cognitive offloading. Over the last few centuries, and accelerating rapidly in the last few decades, our external memory has expanded far beyond the physical page. It grew into sprawling public libraries, then into magnetic media, dense digital storage, and finally culminated in globally interconnected databases that fit in the palm of a hand. And we no longer offload just specific financial ledgers or sacred religious texts. We now routinely outsource navigation, complex calculation, factual recall, and even the intimate aspects of our own autobiographical memory to digital devices. Psychological studies have begun to reveal a clear pattern in how we react to this environment. When people know that information is safely stored externally, and they know it is easily retrievable, they're significantly less likely to invest the cognitive effort required to remember the information itself. Instead, they tend to remember how to find it, where it is stored, and which steps will retrieve it. Our internal operating system is shifting its core function. It is moving away from acting as a self-contained encyclopedia and evolving to function as an index. We are becoming the managers of vast external resources rather than the containers of them. When you instinctively open a digital mapping application to navigate a route you have taken many times before, you are making a quiet cognitive choice. You are choosing to rely on a frictionless external system instead of reinforcing your internal spatial map. Over time, your brain adjusts to that precise pattern of reliance, strengthening some pathways and allowing others to weaken. We are now a species whose knowledge mostly lives outside individual bodies, and that forces us to ask what kind of cognitive core remains inside the skull. Writing and its technological descendants are not simply tools of communication, they function as cognitive prostheses. In cultures with writing, and especially in individuals who become literate, the brain's structure and workload are fundamentally redistributed. Some forms of detailed rote recall are offloaded to the environment, while entirely new forms of analysis, synthesis, and cross-referencing become biologically possible. Just as clay and paper reshaped the brains of the people who learned to use them, today's networked screens provide a new developmental environment. We are only beginning to understand how constant exposure to searchable, scrollable visual streams is actively tuning our attention, our memory strategies, and our neural wiring. If you want to see how a completely different artificial system is being designed to manage patterns, store information, and adapt through training, mirroring some of our own operating system's logic, click the video on screen to explore the architecture of artificial neural networks. And if you want to follow the trail of symbols even further, to see how the same biological hardware that once counted livestock on clay tablets learned to invent algebra, zero, and infinity, watch The Brain That Invented Numbers, From Stone Tally to Infinity. It is the story of how a primate brain built the idea of number, and how that idea now quietly governs every price, every clock, and every risk you navigate every day.